Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic is a self-learning topic of basic MOS transistors. By the completion of this topic, you should be able to analyze the structure of MOS transistors and you should be able to illustrate the enhancement mode MOS transistor action. The basic structure of NMOS and PMOS transistors is shown in this slide. The first figure shows the NMOS enhancement mode transistor without application of any external bias. After fabrication, the front cross-sectional view of the MOSFET N-channel enhancement mode is shown here, where this consists of a P substrate. On either side of the substrate is diffused with N-type impurities, forming the source and the drain. And in between, there is a polysilicon gate formed here. This is the basic structure of an NMOS transistor. Then followed by there is an NMOS depletion mode transistor where you can observe the difference between figure A and figure B between enhancement mode and depletion mode. In a depletion mode transistor, the channel between the source and the drain, the N-type channel between the source and the drain is implanted during the manufacturing process. Whereas in an enhancement mode transistor, the channel will not exist by itself during manufacturing process. After application of a minimum gate voltage that is greater than the threshold voltage, the channel will be formed. And the last figure, that is figure C, shows the enhancement mode transistor only, but PMOS, which consists of N-type substrate and other side of the substrate that is doped with P-type impurities forming the source and drain respectively, and in between source and drain a polysilicon forming the gate. This is the basic structure of a MOS transistor in enhancement mode, depletion mode, NMOS and PMOS. Now let us have a look at the working of enhancement mode MOS transistor or its action, what we can say. Taking into consideration the NMOS transistor with P-type substrate and doped with N-type impurities on either side forming the source and the drain, and a polysilicon forming the gate. As we have discussed in the previous slide, for an enhancement mode transistor, the channel will not be implanted during the manufacturing process, but it will be formed after application of a certain gate voltage. So to understand this MOS transistor action, we are dividing the working into three cases. Case 1, where VGS, that is gate to substrate voltage, is greater than the threshold voltage VT, and VDS is equal to 0. That means there is no potential applied between the drain and the source. What is the transistor action is, the channel is formed, but no current flows between drain and source. So gate voltage has reached a minimum voltage required to form the channel, that is called as the threshold voltage. But as there is no potential difference between drain and source, there will not be any current flow between source and the drain. Whereas in the second case, we consider VGS is greater than VT, that is the channel is formed that helps in forming the channel, and we have applied a potential between drain and source which is less than VGS minus VT. VGS minus VT refers to the effective voltage that has been applied at the edge of the source to form the other than that is taken to form the channel. VGS minus VT refers to voltage required to form the channel. VGS minus VT refers to after forming the channel, how much of gate voltage is left over that will be appearing at the edge of the source. Whereas VDS is the voltage applied between drain and source. So in this case, the drain current increases linearly with VDS. As there is a potential difference, the current starts increasing. When VDS is increased, the drain side becomes more reverse biased, hence more depletion region towards the drain end. This drain end will become more reverse biased and results in more depletion region because of this condition of VDS less than VGS minus VT. VGS minus VT is the effective voltage at the source side. VDS is the voltage that is less than VGS minus VT at the drain side. Hence, this will be more, this junction will be more reverse biased compared to this junction, forming a larger depletion width. Case 3 refers to VGS greater than VT, that is minimum voltage required to form the channel. And here VDS, the applied voltage at the drain side, is greater than the effective voltage at the source side. So in this condition, we call this as saturation region. This condition, the drain current remains almost constant. Why it remains almost constant means as the drain current is increased beyond VGS minus VT, this side the voltage is increased more than this one. The pinch off point starts to move as the depletion region is increasing. So this point starts to move towards from drain end towards the source end. So in that case, what happens after certain amount of voltage is increased, even if the VDS is increased beyond that one, the increased voltage will get dropped in the depletion region as the depletion region will consist of immobile ions. So all the voltage will be dropped in the depletion region, leading to a constant current that is known as saturation region. So in this operation of MOS transistor action, the typical threshold voltage, that is the minimum gate to source voltage required in order to form the channel, will be typically 0.2 times VDD, the supply voltage. So from this lecture, you are expected to solve few of the lecture level questions which are presented in this slide. Thank you. Happy learning.